Okay, first off, sorry about having to do this, but I have to kind of take care of my mother right now with everything she's going through. So I'm just kind of stuck doing things this way. Hopefully this gets fixed relatively quickly so we can go back to meeting in class at the regular time. I'm working on multiple ways to pull that off, but for right now we're just kind of stuck. But as far as it goes, so far we have looked at double integrals, and we started by having a rectangular region R, and don't worry about the rest of this picture right now, but we had a rectangular region R, and then we had to find a way to partition that region R using rectangles. And then once I had that partition, I could set up a sum using rectangular prisms to find the volume underneath some plane or some surface in R3. And that turned out to be a double integral. And we had ways using Frobenius theorem to actually solve that double integral out. And then we generalized from a rectangular region to a non-rectangular region, which I actually called a disk D. But the principle was essentially the same. Find a way to partition the region, and then, well, determine if it's what we called type 1 or type 2, which was similar to an argument you make in Calc 1, which dictated the order that you integrated and set up your double integral. And then we just went back to our same tricks of integration. And then from there, we looked at some applications of integration. I think we did volumes between two surfaces, or between two planes. We did average value of a function, and we said that I can use a double integral to find the area under a curve in R2. And I had mentioned that there are other real-world applications like moments of inertia, centers of mass, and stuff like that. And I might give you some of those for homework, and you can work through them. But ultimately, for those type of applications, similar to some of the other ones we've looked at, you would essentially have a formula to work with, and the problem would really just be setting it up, maybe setting up the limits of integration, and then just evaluating the integral, which, using your understanding of integration and your tricks of integration, all of you can do. So I'm not really worried about those. If you do have questions about any of them, if you look over them, or if I give you some for homework and you're not sure how to do them, feel free to email me. I would say stop by my office, but it's unlikely any of you are going to stop by at 8 o'clock at night, which is when I'm actually making this right now. So just email me, and I'll gladly walk through it. I'll make another video going through it. But the kind of natural question becomes, I have a single integral, which finds the area under a curve in R2. I have a double integral, which finds the volume underneath the surface in R3. And we finished last class by saying, well, if there's a double integral, can I do a triple integral? Well, the logic, I mean, frankly, without thinking about the math, sure, just add another integral symbol on the end and kind of go from there. More than likely, we understand, without even setting it up, that, well, that would then mean that I have three variables. If I have three variables, it means I'm integrating a three-variable function. The problem here is, if I integrate a three-variable function, the graph of that function actually exists in R4, which means we can't actually visualize it. So we can't really graph these things out, and to say we're using them to find something, an area under a curve, a volume, or something like that, is somewhat nonsensical. We will look at some applications using these things, but essentially here it is more an understanding algebraically and a little bit of geometry using that picture of what's going on, and generalizing that which we did for double integrals. And as far as it goes now, while the graph of the function, it will exist in R4, the region that I'm integrating, which I think your book calls R again, will exist in R3. Again, keep in mind, for our double integrals, the graphs existed in R3. The region, the rectangle that I integrated, was in R2. Same idea here. If I'm going to integrate a three-variable function, that graph exists in R4, but the region I'm integrating over exists in R3. And that's actually what this is, where if we find the correct colors to use, I'll go with the black one. My region R, this is X, so just like before, we'll start with a rectangular region, x will range from a to b. Here, the y values, we'll say it's from here to here, just so you can see them, goes from c to d. Then when I project up into the third dimension, we will say, just because it's easy, that's my bottom z and this is my top z. And we'll just go with e to f. And essentially, again, in R1, I just get a line segment. In R2, line segment cross line segment gives rectangle. Now I'm in R3, line segment cross line segment cross line segment gives me this rectangular solid up here as the z's range from top to bottom. This projects upwards, which really means I don't want to draw on this too much, but for the purposes of this now, this is my R, this rectangular solid. And now I understand the concept here. I'm going to be finding a hypervolume, I don't really know, for something in R4, but what I'm going to do is, we'll partition this region here, just like I partitioned the rectangle before, partition this, and then I'll essentially multiply by the function value, the fourth dimension. Here I multiply by the function value to get my third dimension, area under a curve, multiply by the function value to get the second dimension. So we understand the concept. Now I just need to know how to partition this, but I don't want to mess this up because frankly it looks pretty good based on my ability to draw. But we understand the concept. I'm just going to partition everything here with rectangular slices this way, and then I'll slice this way. And again, I'll slice, and I will eventually get a bunch of rectangular solids. And they'll kind of all be jammed in there. And now I have my partition. And then if I want to approximate the value of this Riemann sum, again, before we called it an area over volume, it doesn't make sense really here. So we'll just say, if I want to approximate the value of the resulting Riemann sum, well, I know how it works. It's the summation, as I goes from 1 to n, of the function value, f of x sub I star, y sub I star, z sub I star, times my region, which in this case is three-dimensional, so that will be delta vi for a volume. But then I understand, just like when I used this rectangle before, this delta vi is all these cubes, which obviously will change, but the delta vi is just delta xi, delta yi, delta zi. And again, I understand ultimately, because I know how this is going to work, that will become a dx, dy, dz, a triple integral. But, well, while this will approximate the Riemann sum, how do I make that approximation better? I just take the limit as the magnitude of the partition approaches 0, and then this becomes exact, and it becomes the triple integral that I want. This triple integral, again, we established this is important. This triple integral is over a rectangular region, and it will be just f of x, y, z delta v. And then the only real question that we have is the exact same question we had when we were talking about regions in R3, in our double integrals. How do I evaluate that? The good thing is, as I've said before, we have Fubini's theorem for rectangular regions, for double integrals, and we can really just generalize here. And let's see, for Fubini's theorem, for a double integral over a rectangular region, it became the region from a to b to c to d of f of x, y, z, and then since a and b are first, that's dx, and then second was dy. And then if I wanted, we said I could actually flip these and I could do dy dx. Because it's rectangular, all of these limits are constant, so I can rearrange the order of them. Here I have a rectangular region, so again, all my limits are constants, and I can then evaluate this as the integral. Here I'll alter them. A, B, C, D, E, F of f of x, y, z. And then E and F are z, so that's dz. C and D are y, so that's dy. A and B are x, so that's dx. And now I have my triple integral, my triple iterated integral. And I do stress, I'm not going to fill up the entire board writing these out, but since these are constants, in the same way as with the double integral, I could do dx dy or dy dx, I can alter my order of integration here with no trouble whatsoever. Just alter the order of those constants of integration, constant limits of integration. And obviously, there's actually 6 different versions of this. dz, dy, dx, dz, dx, dy, etc., etc., etc. I had mentioned in class, at the end of last class, that one of the things you can do to test yourself to make sure you're doing it right, there's 6 different orders you can do these integrations in. Do all 6 of them. Make sure all 6 give the same value. If you're doing it correct, they have to. If somehow they don't, then you know you did something wrong. And I do stress on exams, that is absolutely something I'm going to have you do. I would more than likely, as I said in class, allow you to plug it into Maple rather than solving 6 triple integrals out. But I would care about your ability to rewrite these integrals in different forms and set them up correctly, because we established in class the biggest issue, given that you all know how to integrate, is getting all your limits of integration correct. To set up one quick example, I will also point out, as far as the wording goes here, again, before we would say find the volume underneath this, or find the area underneath this and that, or find the area between these two things. We don't do that anymore because, again, it doesn't really make sense. So a lot of times we'll just say, find the triple integral of f of x, y, z equals, here we'll just go with xy, nice and easy, over r equal to 0, 1, cross 0, 1, and just for fun, cross 0, 2. Where, obviously, that's x, that's y, and that's z. So now I have my region. We established before we want to be able to write out these regions in set builder notation. That will go a long way towards simplifying this and making sure you're doing it right. So again, we can just as easily say R is the region XYZ, such that 0 is less than or equal to x is less than or equal to 1. 0 is less than or equal to y is less than or equal to 1. 0 is less than or equal to z is less than or equal to 2. Now set up my integral. I'm not going to bother to take the time to draw out that region and all that. And I get the triple integral over R of my function xy dv is equal to the triple integral. Since it's rectangular, I can do it in whatever order I want. I'll just do a reverse order. 0, 2, 0, 1, 0, 1 of the function xy. And 0, 1 is on the inside, which I'll say is dx, then 0, 1, which is dy, then 0, 2, which is dz. Make sure order of integration here lines up with those there. Outermost, etc. You all know how this works. Now, just solve the integral. And I'll do this one really quickly because then you all know how to integrate. That becomes the triple integral, 0 to 2, 0 to 1. Integrate this with respect to x, you get x squared over 2y, evaluated from 1 to 0, dy dz, which is the integral from 0 to 2 of the integral from 0 to 1. If you plug in 1, that's 1/2 y. If you plug in 0, you get 0. So that's y over 2 dy dz, which is the integral from 0 to 2. Y over 2 with respect to y is y squared over 4, evaluated from 1 to 0, dz. Again, I get the integral from 0 to 2. If I plug in 1, 1 squared is 1 over 4. Plug in 0, you get 0. So that's 1/4 dz. Integrate that with respect to z. You get z over 4, evaluated from 2 to 0. which is 2/4, allergies, 2/4 minus 0, which is just half. And again, I do stress, these are straightforward and simple. Yes, you can randomly throw different types of integration in there based on the function you're integrating. All of you can do that. But the integration part, you know how to do. Given that it's a rectangular region, the limits are constants, and then it's really just do the integration you know, but do it 3 times on every single problem. Unless you're told to integrate all 6 different forms of this, which means do the integration you know and do it 18 times on each problem. You do need to do these by hand, and I will make you do them by hand for homework and on exams. But again, for times when I give you longer things like that, rather than having you do 6 different triple integrals, so 18 different types of integration, more than likely in that instance, I'll just say, throw it into Maple and save yourself some time. But just be aware of the distinction there. But we all kind of know where this is going. It is absolutely great if I integrate and the region that I integrate over is a nice rectangular solid. But let's face it doesn't have to be. In the same way that in R3 before, the region in R2 that we integrated over for our double integrals could be rectangular, but it didn't actually really have to be. So then, what happens if the region that I integrate over is non-rectangular? Well, we already kind of get the idea from what I did with double integrals. I will stress from a notational perspective, we write the triple integral over f of x, y, z dv. Again, I stress, if that's an R, it implies a rectangular region. Your limits better be constant or there's a problem. If it's f, it means it's a non-rectangular region, which means we understand from what we did with double integrals, your limits of integration are probably going to have variables in them. The only question becomes, how do I figure it out? When I had my double integral, the region that I integrated over dictated, I think we had type 1 or type 2. Some regions could be both. If it could be both, then you could pick the order that you wanted, whichever one seems simpler, and then solve the integral. Find your limits appropriately and solve the integral. If that wasn't true, sometimes a region had to be only type 1 or type 2, and then you had to integrate a certain way. It's the same idea here, only expanded on. And the way it works, I am not going to go into incredible depth here on this because, frankly, even if I was doing this live, you people would be bored to tears before I got to the end of it, because it's the same principle as what we did before. So I want to kind of gloss over it a little bit, but make sure we understand the concept because it is fundamentally important. So first, for my region F, again, when I had a double integral, I had a type 1 or a type 2, based on whether it was always 1x over another x or 1y over another y. Well, now I have 3 regions, so I can have what's called z simple, x simple, or y simple. And the idea, we're going to start with the z simple because they're the most common, at least in how we think about it. A region is z simple if whatever the region f that I'm integrating over, there is always some z on top. I won't even write it. Some top and some bottom. And if the region always has a top and a bottom, then I say it's z simple. The other way we talked about this when we did our double integrals was, imagine a line shooting through your region, and if it always entered at, say, one x value and ended at another x value, even if that was function here, then we said it was one type of region. If it always entered here and exited here, it was the other type of region. These are 3-dimensional, so the idea is similar, but maybe slightly different. If the regions that I'm integrating over, say these are the top and bottom of the region that I'm integrating, It is z simple if I can essentially shoot a line going upwards because it's z, and I always enter along this bottom curve and exit along the top curve. Then it's z simple. And then my integral right here is equal to the double integral over d of the integral, we'll say g of xy, h of xy, of f of xyz, dz, dA. Essentially, this is my top, my z sub 1 maybe. This is the bottom, z sub 2. And I'm always entering at the bottom, exiting at the top. So I just integrate my function with respect to z first. But that still leaves me with a double integral on the outside. But this is a double integral over an arbitrary region D. And I will stress that, which I also stressed in class. If I use an R there for either the double or the triple integral, I am assuming and essentially stating that my region is rectangular, my limits are constants. In general, I just write D for a double integral or F for a triple integral, which does not mean my region is not rectangular, and we'll probably do an example where it is, just so we're clear. It means I don't actually know, so I'm writing the general form. It may turn out to be rectangular, but I don't actually know, so I just have to write the general form. But now, I know how to integrate this inner thing. It's just an integral with respect to z. Integrate, plug in my functions, which will give me a really convoluted thing on the inside, but I'll end up with a function in terms of x and y, and then I'll just have to do the double integral of that. But then we understand how the double integral works over a region D. I determine if that region is type 1 or type 2. That then dictates if I integrate with respect to x first or y first, and then I kind of go from there. So all I really do is here, I start by determining what type of simple region I have. Z simple, X simple, or Y simple. We haven't covered those yet, but I'm sure the idea is clear. Once I determine what I have to integrate with first, then I'm left with the double integral, and then I go back to my previous ideas about type 1 or type 2. Keeping in mind, again, although I'm sure it's clear, this will not always be with respect to X and Y. If I have, say, an X simple region and integrate with respect to X first, then this will be a region in Y and Z. And I'll have to determine if it's type 1 or type 2 with respect to Y or Z. And again, the principle is straightforward. It makes sense. It really just comes down to that which I had said in class, working with it and figuring out what are my limits, what type of region do I have, and what limits do I then need. Because the rest of this is just integration that you all know how to do. So, I want to look at a few examples to make sure we're clear on what to do. So suppose this one appears to be dying too. Let f, no, not my function yet. Let f be contained in R3, my region F, in the first octant, where x, y, and z are all positive, obviously, bounded by the coordinate planes, the x, y, and z plane, which will make sure it's always positive or greater than or equal to 0, and the unit sphere, x squared plus y squared plus z squared equals 1. So, if I actually graph this, I'm restricting myself to the first octant, and it's the unit sphere. So these are my points 1, 0, 0, 0, 0, 1, and 0, 1, 0. And then I just have the sphere. I only have part of the sphere, 1/8 of the sphere, this chunk of it in the first octant. And then, like I said, I'm bounded by the x-axis, y-axis, and z-axis, so I get that chunk right there. And keep in mind, my f now is this whole region, that whole three-dimensional region, which is clearly not a rectangular solid. So now if I want to integrate, and I will integrate the function, I want to find the triple integral over that region F of 2xz dv. So now, what's the first thing I do? Figure out if that's x simple, y simple, or z simple. We have only gone over z simple for right now, so the idea, bottom is obviously right here where z is 0. If I shoot a line, I'm running out of colors. If I shoot a line upwards through z equals 0, I always enter the floor at z equals 0, and I exit someplace up here on the sphere. Which means it's z simple. I always start on the bottom and go up to some point on the top of the sphere right there. I would also point out, because it's a sphere, we understand the concept. I could have actually shot left to right or even front to back. So this, because of its shape, is actually x, y, and z simple. So this one can be done multiple ways, but we're deliberately only doing z simple for right now. But then, if it's z simple, I need to find my limits on z. Clearly, 0 is less than or equal to z is less than or equal to, well, the upper limit is the sphere, so I do exactly what I did before. I take the sphere and I solve it for z. That's my upper limit. So I get z equals 1 minus x squared minus y squared, then square root it. Normally I would get the plus or minus, but I've restricted myself to first octant, everything positive, so I can drop the negative. There's my upper limit on z. So I write that out. 1 minus x squared minus y squared. Now I know this is equal to the integral, or the double integral, of the integral from 0 to the square root of 1 minus x squared minus y squared of my function, which I wrote right there, 2xz, dz, dA. Now I just need to figure out what this is. Is that a type 1 or a type 2? And I would actually stress, if it's not clear for this one, it's a sphere, it's going to be both. But for the purposes of this, the way you find it in general, I have essentially dropped z out of the equation. I did top minus bottom, so now I drop into my other two regions, which in this case would be the xy plane. And then you do not have to do this, but I would encourage you to do it because it helps me, not being a visual person. Draw your graph. So now I'm in the xy plane because I've gotten rid of z right here. Now look at your region in the xy plane. And all I do is look at my region, x squared plus y squared plus z squared equals 1. Those are my bounds. And since I flattened into the xy plane, just drop the z from the equation because it's 0 now. That's my new region. I only want where it's positive, so I'm only in the first quadrant. And now I need to integrate that region. That's my D now. Again, clearly that's type 1 and type 2. I can pick the order that I want. I think in my notes, I went with next taking limits with respect to y and going up and down like that. So then clearly based on this, if I have this equation right here, solve it for x. I think I might have solved it for x. It doesn't matter. Nope, I solved it for y. If I solve this for y, I get y is 1 minus x squared square rooted. Again, I can drop the negative because I'm in the positive quadrant. So then on this region, what are my limits for y? 0 is less than or equal to y is less than or equal to the square root of 1 minus x squared. And then my x limits will be constant. 0 is less than or equal to x is less than or equal to 1. And again, I stress, and we stressed in class, my last limits have to be constant. If they're not, that's a problem. But now, two things. First, write out your region. And I do write it out in step-builder notation. And again, I do stress, even if you don't want to do it, you're going to do it on your exam. It is important. So make sure you're doing that. So I get f is equal to the region xyz such that 0 is less than or equal to x is less than or equal to 1, 0 is less than or equal to y is less than or equal to the square root of 1 minus x squared, 0 is less than or equal to z is less than or equal to the square root of 1 minus x squared minus y squared. And the reason for that, now I can create my triple integral. And I get the integral of 2xz dz dy dx. X's range from 0 to 1. They're constant. They're on the outside. That works. Y's range from 0 to the square root of 1 minus x squared. Z's range from 0 to the square root of 1 minus x squared minus y squared. Now I have an integral to solve. And I'm not actually going to do the integration there. That's really easy integration and plug stuff in. The actual answer, I have it here. If you do all the integration, you should get 2 over 15. So work through the integral like we would in class and make sure you get the answer that you should. Now I take a drink of Mountain Dew like I would in class. And hope it doesn't make my allergies set off and make me cough again. But I want to do maybe one more of these just to set it up, to understand how to set up our limits. And then we're going to look at a few applications, although I might break that up to a separate video. I haven't decided yet. So suppose I have this. Nice, simple function. Make sure that's lowercase f so there's no confusion. F of x, y, z equals y over the region f, which is, again, the first octant. And these do not have to be in the first octant by a rule. I'm doing it to keep stuff positive for now, but they don't have to be by a rule. Bounded by z equals 3 minus x equals 0, y equals 0, y equals 3, and z equals 0. And again, the x, y, and z equals 0 bounds will drop me in the first octant. So I want to integrate this function, and I do stress, like I said in class, understand the function you're integrating over, which is just the thing you're going to plug in there into your integral, versus the bounds, which are also functions that you will use to create your limits of integration. Make sure you keep the two things straight and don't get confused. So that is just going to float through the problem. My ultimate goal is to find the triple integral over f of the function y dv. Now I just need to figure out my f, which will then give me my limits. First thing I do, graph it. And let's see if this graph comes out as nice as the one in my notes. So let's see. X is 0, y is 0, y is 3. So that's like right here. And that will shoot all the way up. Z is 3 minus x. So when x is 0, which is all along the y-axis, z is 3. So I get this. And then clearly this limit will cut right there. And I'll get to that corner. This is z equals 3. And then the plane 3 minus x, it doesn't involve y. But as I shoot along the x-axis outwards this way, it will come steadily downwards. Until right here. Which, up to my ability to draw, almost hit it. Pretend that's straight, even though I made it curvy, so it would hit. That's obviously x equals 3, because when x equals 3, z is equal to 0, that's when I hit the floor. And I get a ramp. And if it helps, again, this is where y equals 3, so this whole side of the ramp is the y equals 3 plane. The top right here, the ramp itself, is z equals 3 minus x, right there. That's my plane. And then this is x equals 3. And I would point out again, there are probably different ways to view this as x simple, y simple, and z simple. Frankly, if we were in a seated class, I would do what we did last week and simply break you up into groups and say, figure it out if it's z simple or x simple or y simple. But just to see the different ways to write this using something other than z simple, here we're going to go with x simple. Because from the x-axis perspective, if I start on the back right here, I always enter on this back wall, the back rectangular wall right there. And I always exit on the ramp itself, which means going forward, I always enter on that region and exit on this region. So it's clearly x simple. Yes, I always enter on this part on the left and this part on the right. So again, there's different ways to do this. For right now, we're going to say it's x simple. But that tells me this is the double integral over d of the integral. I need to find my limits on x of the function, which is y, dx, dA. Now I find my limits. But the back wall where I enter is always x equal to 0. So 0 is less than or equal to x is less than or equal to. Well, I always enter along the ramp, along the plane. So solve that plane out. Solve it for x, add the x, subtract the z, and I get x equals 3 minus z. So there's my first limit. And now I have my limits of integration. 0 to 3 minus z. Now I do the exact same thing. I have eliminated the variable x, so now I drop into the yz plane. And in the yz plane, that's y, that's z, if I get rid of x, which is here, well, the yz plane is right back here. And that's clearly just a rectangle. This wall right here, I've eliminated this direction coming out, so I can flatten that way. This is the point 3, 3, and I get the rectangle. And again, this is what I had said before. We use this notation because I don't know what this region is. As it turns out, the region ends up being rectangular. So my limits are really easy. 0 to 3 for y at z. And then I can write out my region f. It's the set of all x, y, z, such that, let's see, y goes from 0 to 3. You can write these in any order. Tend to do them in reverse order of the way you're going to integrate, so you can read them off. And then z goes from 0 to 3. And then x goes from 0 to 3 minus z. So now I can set up my triple integral. Let's see. That will be a function y. We said integrate with respect to x first. Then if I do these in reverse, then it will be z, then it will be y. Limits on y are 0 to 3. Limits on z are 0 to 3. Limits on x are 0 to 3 minus z. And I have a nice integral that I can solve. Once again, all of you can integrate that. That's not that hard. If you actually integrate it, the value ends up being 81 over 4. So check that and make sure you can get it to work. And then if you're so inclined and have the time, see if you can write the integral out as a z simple or a y simple region, and make sure you get the same value. But once we understand the trick, and I am aware, as I also said in class, part of doing these just comes with practice. So practice. You will have homework. You have problems in your book. Just practice and get used to setting up the limits of integration, because that's the hardest part. But we also have applications. And for right now, the only real applications that we need are the applications we've done before. Before, we said, if I do the double integral over 1 dA, that ends up giving me the area under a curve in R2. So the double integral, which normally gives me a volume, actually gives me an area if I integrate the function 1. So I can do the same thing here. If I do the triple integral of 1 dV, this gives me the volume in R3. Which, if you're paying attention, means, well, now I have different ways to solve all these problems and kind of test myself. We used a double integral to find the volume underneath the surface. Now, if I integrate the function 1 with a triple integral, I can also get the volume. And again, it is debatable which is easier. We saw with the double integral as area under a curve, it would make much more sense to just do the single integral. Same idea here. If you can set up the triple integral to get the volume and integrate 1, then you could just set up the double integral and solve it that way. But again, different ways to check yourself. And speaking as an instructor who may want to just randomly mess with you on an exam, also kind of a fun exam thing, find this volume using a double integral or a triple integral, testing to make sure you understand what these things are. But then once I have this concept, the other thing we looked at was average value of a function. And before, we said the average value was the double integral over d of f of x, y, dA over the double integral of d over d of 1 dA. The double integral over the area of the region I was integrating over. But I can do the exact same thing here. The average value of a function is the triple integral over f. We have to use the general form because I don't know my region, of f of x, y, z dv over the volume of the region I'm integrating over, the triple integral of f of 1 dv. And I'm not actually going to run through examples again, mostly because this video is already almost 45 minutes long. And if you're still watching and paying attention, I don't think you're going to watch and pay attention for another 10 or 20 minutes as I work through some more examples. I do stress, if you would like me to work out more examples, I have absolutely no problem doing that. I would also point out it's close to 9 p.m. now, and it's really pitch black outside my window. I also have no problem, if you had questions, stopping by for some reason, if you wanted to stop by late at night, because you're free to ask questions. But hopefully this will not last long. But for right now, it is what it is, trying to coordinate everything and making sure you people get as much information out of this as I can possibly give you, so I'm kind of stuck doing it this way. I will send more information through Blackboard and all the other things we're going to do to help. Also, again, if you would like me to make more videos going through examples, feel free to email me, let me know, and that will work fine. That should be all for now.